Hey there, fancy seeing you here. Just kidding. Hey guys, how's it going? This is going to be part 2 of the Algebra 2 final review. This part covers radicals and statistics and a log or two that I forgot from part 1, so my bad. But let's hop into it because we sure have a lot of stuff to cover per usual. Yeah, so let's hop right into it. So problem number 1 says graph the following. F of x is equal to log of x plus 2 minus 3. Now, do not fear, I am here, okay? I know we've forgotten like everything about graphing, but let's jog our memories, okay? Logs and exponentials are inverses. Exponential functions do something like this, well, if it's growth. And if they're inverses, they undo each other. And this is the worst drawing I have ever drawn in my life. Holy guacamole. That is terrible. Let me get my life together really quick, guys. So if we had, let's do this. If we had an exponential growth, let's just say it did something like this. Right, there's our exponential function. And since exponentials and logs are inverses, y and x switch. So what happens is that point gets switched and our graph looks a little something like this. So exponential functions, the one on the top, have a horizontal asymptote. That all goes away when we become a log function, and instead we swap it out for a vertical asymptote. So our log functions are going to look a little something like this graph I'm highlighting over here on the right, and they have a vertical asymptote. So we've got log base 10, I guess, if you wanted to throw in the base there. Any log without a base is base 10 of x plus 2 minus 3. So we're going to have to determine our vertical asymptote. And remember that our vertical asymptote, I kind of drew it over there, is vertical. And so it crosses the x-axis. Well, it doesn't cross, but it like hits the x-axis at some point, which means it's an x equals equation. So to find our vertical asymptotes for logs, we set the exponent, we set the parentheses equal to 0. We set the argument equal to 0. So this is going to become x plus 2 is equal to 0. And we'll find that our vertical asymptote for this log function is -2. X is equal to -2. And that makes sense because like literally this x minus 2 part right here would tell us that that's a horizontal shift left 2 units. And so where our normal vertical asymptote would have been at 0, it's been moved left 2. So let's go ahead and draw in our asymptote at -2. So we have a vertical asymptote. And I like to always label mine vertical asymptote x equals -2. Then in order to draw our graph, we need to determine 2 key points. This is going to become x and f of x. I'm just going to rewrite it. So we want to use a couple properties that we know. We want to use log base b of 1 is equal to 0 because anything to the 0 power, right? Anything to the 0 power is 1. That's why we want to use that property. So our goal is to make the inside parentheses equal 1. How can I make x plus 2 equal 1? And if you're not sure, you can literally just solve when will x plus 2 equal 1. You'll get x is equal to -1 by subtracting 2 on both sides. And so if x is -1, then f of -1 gives us log base 10 of -1 plus 2 minus 3. That's really log of 1 minus 3, but we know that log of 1 is equal to 0, right? From this property, log of 1 is equal to 0. So that becomes 0 minus 3. So we get the point -3. So this x equals 1 is the coordinate -1, -3. That becomes literally -1, -3. And that's the point that we're going to plot on our graph. So find x is -1, y is -3. We have that point right here. Then we're going to repeat the process, but now we want the inside of the parentheses to equal the base, because the base to the first power is equal to the base. So I want my parentheses, I want my argument, x plus 2, to equal my base. Remember, this is log base 10. So if I solve this, I'll end up getting x is equal to 8. And if I evaluate my function, f of not -8, my bad, f of positive 8, that's going to give me log of 10 minus 3. But we know log of 10 is equal to 1. So that's 1 minus 3, which gives me -2. Therefore, I end up with the point 8, -2. So we'll plot 8, -2, and sketch our graph. So our graph has to approach our asymptote and go through these 2 points. Now this was important because we're going to evaluate the end behavior in just a minute from this function. So again, we see that we have our vertical asymptote is -2. We're going through the point -1, -3, 8, -2. Now the purpose for this is because we've got to determine the end behavior of this function, and you're not going to be given a graph. So you're going to need to know how to graph a log function just like this. And we can determine the end behavior on the left and the right. And if we're looking at the multiple choice options, you'll notice that it says as x approaches infinity, as x approaches infinity, as x approaches infinity, as x approaches infinity first, right? Remember that as we're talking about as x approaches infinity, that means we're talking about the right end behavior. And the reason for that is if you think of this x-axis as a giant number line, over on the left is -infinity and over on the right is positive infinity. So whenever we say as x approaches positive infinity, that means we're talking about the right end behavior. And we want to know, where does our function, where does the y values go? That's what this next statement is. We have to determine if it's going to positive infinity, positive infinity, positive infinity, positive infinity. Well, it looks like there's really no other option. X is approaching in all of these positive infinity, right? Positive infinity, positive infinity, positive infinity, positive infinity. And if we look at our graph, right here, here's our log graph. I'm going to do it in a different color. I'm going to do it in black. Here's our log graph, right? Although it looks like it's kind of flattening out, there's no asymptote that's stopping it. So if we zoomed out, it would eventually slowly keep growing. It's just going to take a really long time to do so. So that makes sense that as x approaches infinity, the function is increasing. It's slowly going up. So that makes sense. That's the right end behavior, though. That's over here on the right. What about on the left? So for the left end behavior, we're talking about over here. The left end behavior would be as x approaches negative infinity. And we'll look and see x approaches -2, 2, -2, 2. Oh, crap. And my graph is not defined over here. So actually x approaches negative infinity does not make any sense because there is no graph over here. There's no log graph chilling over here. There's no log graph over here. So negative infinity doesn't work. That's too far to the left. Too far to the left. Okay, well, Let's keep going then. All right, there's no graph here, no graph here, no graph here, -5. Oh, our graph is going towards my asymptote. So on the left, end behavior, as x approaches our asymptote, -2, we want to know where's our function going. And the reason we want -2 is because that's where the asymptote is, and our graph is not defined past that point. Our graph is not defined past that point. So we can immediately eliminate two of our options. It's not going to be this guy and it's not going to be this guy because we want the left end behavior approaching our asymptote at -2. So now we just have to ask ourselves, where's our function going? And since our function is pointing down on the left, that means our function is going to approach -infinity because it's pointing down. So the only option that matches that is A. Number 3 says solve for x and check for extraneous solutions. So we have a radical is equal to -2x, and then an option for us to check our work here, make sure we don't have any extra line solutions for us. So in order to check for extraneous solutions, we're going to need to square both sides using properties of radicals. Squares undo square roots, leaving the radicand. So this gives us -x plus 3 is equal to -2x times -2x. And the reason I encourage us to do that is so that we don't forget that -2 times -2 is +4, and x times x is x squared. So now that we have, and our goal is to solve, we have -x plus 3 equals 4x squared. Remember, we have to solve, and we have an x squared. That means we're going to need to factor. So move everything to one side. I like to keep my x squared positive, so I'm going to add x and subtract 3. Add x and subtract 3 to both sides. So now I have 0 is equal to 4x squared plus x minus 3. And if you try to factor this, it's a little tricky. You're going to have to use guess and check, which works. You could say, okay, what are the factors of 3? It's just 1 and 3. And the factors of 4 are 1 and 4 or 2 and 2. And you can see what factors will give you positive x in the center, which you might notice it's 1 and 4 and 3 and 1. It would be 4x. X, and then 1 and 3. If you have +1 minus 3, you will end up with 4x squared plus 4x minus 3x minus 3, and that becomes exactly what we wanted to factor. Or if you don't remember guessing and checking and you get confused a little bit, you can also use multiply, divide, slide. So I'm going to show that as well, in case you forgot. So whenever, and we always used multiply, divide, slide whenever there's a number in front of our x squared. So how we simplified this problem with multiply, divide, slide is I took 4 and multiplied it to the last number. That gave us -12. Simplified this to x squared plus x. So that's the multiply part. Then we needed to factor this expression. So what multiplies to -12 but adds up to 1? That's going to give us 4 and 3. And x would be positive, 4 would be positive, 3 would be negative. And since I multiplied, now factored, now I have to divide by the number I multiplied by, because I completely changed the problem. So I've got to divide by 4 on both numbers. And if it divides nicely, let it. If not, then we're going to slide. So this gives us 0 is equal to x plus 1 times 4x minus 3. This guy's going to slide in front. And notice that that's exactly where we were last time. 4x minus 3 and x plus 1. I'm going to just slide all of this up here. Whatever method works for you, knock yourself out. But we really have 0 is equal to x plus 1 and 4x minus 3. We haven't finished. So by the zero product property, set each factor equal to 0, and you'll get x is equal to -1. And I'm just going to show this one, 4x minus 3 equal to 0. Get 4x equals 3, x equals 3/4. So those are your two options of solutions. And again, we're going to have to check for extraneous solutions. So let's check and see if the square root of negative x plus 3 is equal to -2 times x. And I like to always put parentheses when we're checking. Checking -1 means that we're going to plug it into all of our parentheses and see if we get a true statement. -1 is +1. Is the square root of 1 plus 3 equal to -2 times -1? 2. The square root of 4 is definitely 2. So x equals -1 is certainly a solution. And then we'll repeat the process with our other option. So we're going to check and see if 3/4 works the same way. So is the square root of -3/4 plus 3, get a common denominator, equal to -6/4? Is the square root of -3/4 plus 12/4 equal to -6/4? This is the square root of -9/4. Is that equal to -6/4? And we can see that this is not true. This is really the square root of 9 over the square root of 4. Square root of -9, and that's going to not equal -6/4. So -3/4 is extraneous. All right, moving into the statistics portion. What kind of sample uses volunteers? Give an example of how to collect that type of sample, and is there any bias in it? So we have options of convenient, self-selected, systematic, and random. Convenient would be like you taking a survey at the park. It's convenient for the park goers. It's convenient for you to get people to take your survey and collect a sample from that population. Self-selected would be where you're advertising it somewhere and people volunteer to answer the survey that you're asking of them. So straight away, we know self-selected for sure uses volunteers, but let's keep refreshing our memories and going through the rest. Systematic would be that you have some sort of system to collect the sample, maybe ordering with some sort of numbers, and like maybe selecting every 10th person in the phone book or something like that to give a call and see if they would take your survey. That would be a systematic sample, and a random sample would be that it's got to be completely random, maybe using a random number generator, spinning wheel with random names on it where everyone has the same likelihood of being selected. So a self-selected sample uses volunteers. They are used typically collected by posting a survey to a specific demographic, asking them to partake in it. So, and a couple examples could be a newspaper. We saw this in the Desmos. It could be a newspaper ad where they are asking the readers, the specific readers that read that newspaper, to take it. It could be a TV station ad, and the viewers of that particular TV station are asked to partake in that survey. You could even think of it as like the radio station asking people to take their survey. That might be an example of self-selected. Even just like me, a teacher, if I posted it on Canvas and was like, hey, if you get a chance today, go ahead and take my survey, that would be self-selected, where I'm taking volunteers from the class to take my survey and select that sample. What kind of sample has the least amount of bias? Give an example of how to conduct this kind of sample. So now that we know convenient is one where you are asking people and it's convenient for them, convenient for you, that's not too bad. But it's only based on the location, right? Self-selected has a little bias in it because you're only selecting a certain demographic of the population. You might be excluding the entire population. Systematic has a pretty low amount of bias because you're being very careful about how you're selecting this system, meaning that, or this sample, meaning that you're going through the phone book and selecting every 10 names or something like that. But of all of these, the sample that has the least amount of bias would definitely be a random sample, because everyone has the same exact likelihood. Everybody in the population has the same likelihood of being selected for this. So the ways that we could conduct this kind of sample could be like a random number generator, where say we take everyone in school, put their name into a list and assign them a number, and then we randomly pull numbers and select them to take our survey. That would be something that is a random sample. Also, we could go, if we had a small sample size, a small population that we're trying to survey, we could go real old school and write it down on a piece of paper, fold it and put it inside of a hat, and then randomly pull pieces of paper out of the hat, right? But as long as we're selecting things such that they have the same likelihood, that would be a random sample, and random samples have the least amount of bias. So let's suppose we want to conduct a survey about student movie genre preferences. We will survey a sample of the student population to make inferences about the entire population. Okay, so we're going to conduct a survey and it's about movie genres. And what is the population we are trying to make inferences about? Who are we surveying and who are we trying to make a statistical inference about? And that would be about students. Students, and I mean like all of them. Technically, this survey didn't give us any specifics. So students could be anywhere from a kindergarten student to elementary to middle school to high school to college to doctorate degree. It did not specify the type of student. It just says student movie genre preferences. So it's important to know the population that we're trying to make inferences about. So what might we do to select a sample that represents that population, depending on how we want to select this survey, is we probably want to do something random. We want to definitely use some sort of random sampling of our populations. And let's just say we start locally with our local high school. Maybe we make a numbered list of students at TVHS and pull their numbers randomly, a random number generator, to select a sample population, and then repeat this process for other schools. Yep, so we could make a numbered list of students at TVHS and select students randomly to ask them about their movie genre populations. But since we're talking about all students, then we could repeat this at our other local high schools, right? And then we could even send it out to the middle schools and the elementary schools and the college students and things like that, to start to grab a larger selection from our student population. So same situation, we want to conduct a survey about student movie genre preferences, but now we want to know if we only surveyed our class, would that represent the entire population? And that answer is no. The reason for that is we are going to be asking about all students. So if I ask just our class and our class period at that, that is just a teeny tiny little subset of our entire population. Remember that image we had where the population was here, right? And there are all these dots. This is all different types of students in the population. And maybe these color dots are high school. And maybe there's a sprinkling of elementary dots. Maybe there's some middle schoolers being inputted in there. Maybe there's some college students in our population, right? And if I were to just conduct only a few, right, from high school, maybe this dot right here is my class, this is my class, this is my class, right? If I selected this tiny sample, right, of students, and that was my class students, that is very, very small out of the entire population of students. So that would not represent the entire populations. That's only our class period, which isn't all students ever. We would need to include other class periods in my class, but not even just that. We need to include all students in general. Remember, all schools, all grades, everything is what we want to make a assumption about. So just surveying our class would be a very small part of the all student population. We cannot make conclusions about all students with just our data. It would definitely, most definitely be a biased survey if we only asked our class what their favorite movie genre preferences were. So what should we take into account before selecting the sample about student movie genre preferences? Select all that apply. So we have option A, the sampling method should not contain any bias. And yeah, we would want to make sure that we sample appropriately so that there's the least amount of bias as possible. So yes, I would say that that is definitely true. Therefore, we would select it. The sample must be representative of the entire population, right? Of the student population. That was the whole thing why we couldn't just ask our class. So it should represent the entire student population. So B would also work. The sample size must be at least half of the student population. That could be really tricky to do, considering that the sample size is infinitely big. It's very huge. So we can't always guarantee that. So it's not necessary, especially when we are doing things randomly. So I would not select that statement. The sample should be selected randomly from the student population. Yeah, we were just talking about that. Since we're going to select randomly, everyone has the same likelihood. And that allows us to have a sample that contains no bias in it. And therefore, samples with no biases will be representative of the entire population. So most definitely, our sample must be selected randomly. And lastly, the sample should be one high school math class. Again, no, that's not going to work for us. Remember, that could be our class. That does not represent the entire population of students. So that's not going to work for us. Meh. Okay, the cafeteria is trying to figure out how many students buy lunch every day. So they're going to conduct a survey with 500 students. The results are presented in percentages below. So this is kind of like a frequency distribution table. What number of lunches will be sold next week is the question, okay? So what we're trying to answer is what is the number of lunches that will be sold next week? Let's look at our table. We can see that the number of lunches per week is 0 times, 1 time, 2 times, 3 times, 4 times, and 5 times. And then they just give percentages of students that are buying lunch. So if we're going to figure out what number of lunches will be sold, we need to figure out, well, how many are being sold in general based on these percentages. So to figure out how many are being sold, I'm going to take the number of lunches bought per week and multiply it by the percentage. So we're going to say 0 times 12% as a decimal is 0.12. And if I do 0 times 0.12, that's going to give me, oops, just kidding. That's going to give me 0. What I want to do actually is figure out the percentage of students buying lunch. Here's all of my percentages out of the 500 students. And then I need to multiply it by the number of lunches bought per week. So my bad, hold up, JK. So what we're going to do instead is we're going to take 500, because that's our population of students, times 12%. And our populations of students, 500 times 18%. And take our populations of students, 500 times 10%, and figure out how many this is. Again, 500 times 10%, 500 times 15%, 500 times 35%. So if we do that, 500 times 0.12 gives us 60, so 60 students. 500 times 0.18 gives us 90 students. 500 times 0.10 gives us 50 students. Another 50 students. 500 times 15% is 75 students. 500 times 35% is 175 students. So we know that 12% of 500 is 60, 18% of 500 is 90, 10% of 500 is 50, 15% of 500 is 75, and 35% of 500 is 175. So we just found the percentage of 500 students. Okay. Now, remember, the cafeteria is trying to figure out how many students buy lunch every day. And these are the results from the survey. We want to know how many lunches will be sold. So if a student buys lunch 0 times, then these 60 students are buying lunch no times. That means there's no students buying lunch that week. And if these 18% only buy it 1 time, that means 90 students only buy it 1 time. That gives us 90. And if students buy lunch 2 times, then that means 50 times 2 gives us 100 lunches that they're going to purchase. 3 times is going to give us 150 lunches that the cafeteria has to make. If someone decides to buy lunch 4 times, 75 times 4 gives us 300. And lastly, if someone decides to buy lunch every single day of the week, 5 times a week, they're part of our 35%. That's going to give us 875 lunches for that. Now to figure out the number of lunches sold next week, we're going to have to add up all of those values. So 0 plus 90 plus 100 plus 150 plus 300 plus 875. That gives us 1515 or 1,515 meals. So if the cafeteria wants to know what number of lunches will be sold, it's going to be 1,515. So what we had to do was figure out the percentage of students buying lunch. We needed to find the percentage of the specific 500 students that were surveyed, right? 500 students, we needed 500 times all of our percentages. 12%, 18%, 10%, 10%, 15%, 35%. Then once we got that number, we needed to multiply it by how many times they were going to purchase lunch. 0 times gave us 0, 1 time 1, 2 times 2, 3 times 3, 4 times 4, 5 times 5, and get a number and then add them all up to figure out how many meals that we got. And here's another one. Okay. Another statistic question. Many things are normally distributed, such as heights. The average height of a female is 5'4". Miss P finds that 68% of females are from 5'2" to 5'6". She also determines that 95% of female heights are between 5 foot and 5'8". Part A says to draw a normal distribution curve and label it. What is the standard deviation of the data? So based on this information, we're going to have to draw a normal curve. And since it is a normal distribution curve, right, it says many things are normally distributed, such as heights, right? We already have that it's normally distributed, such as heights. And it says it's also a normal distribution curve. So normal distributions have the mean equal to the median equal to the mode in the center. So since the average height is 5'4", that's the average. It goes in the middle. And we know our curve kind of does, oop, that's a really bad curve. That's also a really bad curve. There we go. It's symmetrical. Okay. And we found that 68% of females are 5'2" to 5'6". So within 1 standard deviation of the mean. This would be 34% and 34%. That's a total of 68% are between 5'2" to 5'6". So that means this is 5'2" on the left, and this is 5'6". She also found out that 95% of female heights are between 5 foot and 5'8". So again, going back to the empirical rule, 2 standard deviations of the mean is 95%. So on the left, that height would be 5 feet. And on the right, that would be 5'8". Based on this, right, we know that this marking over here is -1 standard deviation, and this marking over here is +1 standard deviation. The green ones are -2 standard deviations, +2 standard deviations. Based on the spread from the mean, we know that the standard deviation is 2 inches, right? Or sigma is equal to 2 inches. And that's because the difference from 5'4" to 5'6" is +2, or 5'4" to 5'2" is 2, right? Even from 5 foot to 5'2", that distance from each other is 2 inches. So based on this, we can continue on, right? We had within 1 standard deviation of the mean, right here, all of this shaded region, that is 68%. Within 2 standard deviations of the mean, which is over here and over here, all of this shading is 95%. And within 3 standard deviations of the mean, that's 99.7%. Now that we have empirical rule in our mind, we need to know what heights are within 1 standard deviation of the mean. So since the mean is 5.4 and the standard deviation is, right, remember our mean x bar is 5'4", and we found from the spacing and the distance that the standard deviation was 2 inches. That means that within 1 standard deviation of the mean, that means that we're going to be between 5'2" to 5'6". And if I want to find it within 2 standard deviations of the mean, that's going to be from 5 foot to 5'8". And how I went from 1 standard deviation to 2 is, remember, our standard deviation is 2 inches. So that's consistent throughout every standard deviation of the mean. So 5'2" minus 2 is 5 foot. 5'6" plus 2 is 5'8". If I want to continue on into 3 standard deviations of the mean, I'm just going to add or subtract sigma from those values. So 5 foot minus 2 inches gives us 4'10". Remember, there's 12 inches in a foot, to 5'10". So tying this all into the empirical rule, notice that within 1 standard deviation of the mean was 5'2", to 5'6", and that is 68% of the data. 1 standard deviation of the mean is 68% of the data. So 68% of the data is 1 standard deviation of the mean. These are the heights that account for 68%. 2 standard deviations of the mean gave us heights from 5 foot to 5'8". And 2 standard deviations of the mean accounts for that 95%. So 5 foot to 5'8" is the 95%. And lastly, three standard deviations from the mean gave us the height of 4'10" to 5'10". And within 3 standard deviations is 99.7%. 3 standard deviations is 95%, 99.7%. So these heights are the heights that account for 99.7% of the data. Because of the empirical rule, we know this to be true. So we really were just tying in this original picture right here to the normal distribution and the empirical rule. So right here, this first one right here was 68%. That's why we got 5'2" to 5'6". Then within 2 standard deviations of the mean, we have 95% of our data. So that's where we got 5 foot all the way to 5'8". And within 3 standard deviations of the mean, all the way here to this marking, right? That's 99.7% of our data. That's where we got 4'10" all the way to 5'10". Cool. All right, I believe that does it for part 2. See ya for part 3. Have a great day, guys. Study hard. You can do hard things. Catch you later.